Welcome back to the deep dive. So, we rely on these large language models for more and more complex stuff, right? Summarizing huge piles of research, making sense of legal docs, generating complicated code.
Yeah, they're amazing tools.
They really are. Brilliant, mostly. But sometimes they just aren't. Have you ever tried asking an LLM a really complex multi-step question? Something like, what's the birth date of the lead actor in the movie directed by the person who wrote Dune?
Mm-hmm. A classic multi-hop query.
Right. And you might see something weird happen. The model seems to follow the first step, maybe the second, and then the whole reasoning chain just collapses. It's almost like it forgot everything it just figured out right before giving the final answer.
That specific thing, yeah, that sudden collapse on complex tasks, that's actually what we're digging into today. Our sources look at this from a really foundational angle, and they formalize this, well, theoretical bottleneck that seems inescapable. We're focusing on multi-hop question answering, MHQA. And this kind of task is tough because it demands what's called compositional reasoning. You've got to pull together different bits of evidence, often spread out, and they depend on each other. It has to follow a strict sequence.
Right.
And the key finding here is that the usual way we do things, the single-pass approach, asking the LLM to figure it all out in one go, it's just fundamentally not up to the job for this level of complexity.
So our mission today is really to get under the hood, understand the physics governing this failure. It's not just about better prompts or fine-tuning. It sounds like there are hard limits involved.
Exactly.
Hard limits.
We're going to explore this rigorous information theoretic analysis the researchers did. It formalizes the ceiling, introduces something called the Fano-style accuracy upper bound, and this related thing they call the accuracy cliff.
That cliff is key.
Yeah, we need to understand where that theoretical wall is. And then we'll look at the solution. They propose this multi-call idea, a framework they call InfoQA, which is supposed to be capacity aware. Sounds like a plan. Let's start with that core constraint then. Capacity.
Okay, let's define it.
Right. So we have to start with capacity. Any LLM, it operates with a finite output capacity per pass. Let's call it $2. Think of it like the model's internal thinking space, its scratch pad, the tokens it generates while it's reasoning, plus the final answer. All of that has to fit down a kind of fixed bandwidth pipe.
Okay, like a data pipe.
Exactly. Every single token it generates can only hold so much information. So there's this absolute upper limit on the total amount of new, resolved information the model can reliably carry forward in that single attempt to answer the question.
Okay, conceptually that makes sense. But hang on, the immediate question then is, if it's about capacity, why don't we just use models with these huge context windows? 100K tokens, a million tokens. Doesn't that solve it?
That's a really crucial distinction. The input capacity, how much text you can feed the model, yeah, that's gotten enormous. But this constraint, this dollars, it applies to the output capacity.
Output capacity.
It's the bandwidth needed for the model to actually process the complex reasoning and spit out the final answer correctly. The input context might contain, 1,000 different facts, but the final reasoning chain, the steps needed to connect those facts to get the answer, that chain itself has a finite information density it needs to express.
I see.
So even with a massive context window, if the reasoning needed involves multiple dependent steps, that whole process can still overload the, let's call it, working memory design for that single output pass.
So if the task is really complex, like our 3-hop question, plus maybe navigating through a ton of irrelevant stuff in the context, the total sort of requirement for the task, with what the research calls the information demand, or beta dollars, that demand climbs fast.
Precisely.
And that rising demand, beta, is what bumps up against that fixed output capacity, $30.
That's exactly it. When the information demand load, beta goes past the model's capacity, $3 you get capacity overflow. Basically, the signal-to-noise ratio just tanks. The relevant bits needed for step 1 might get drowned out by the sheer space needed to plan for steps 2 and 3, or just get lost in all the other noise from the context.
This sounds like, a practical engineering challenge, but you said the sources frame it as a hard mathematical limit. How did they actually formalize this?
Yeah, they went to information theory. They looked specifically at how much uncertainty reduction, which is basically information has to be present in the model's output to guarantee you get the right final answer.
Okay.
And from that, they derived this relationship, the Fano-style bound. It mathematically links the task's inherent information demand, that's be a bit deliver, to the LLM's output capacity, $1.
And what's the bottom line of that theorem for us, the users trying to get reliable answers?
Well, the conclusion is pretty stark, and they argue non-negotiable. If the task's demand beta exceeds the model's capacity, dollars, getting perfect accuracy, like accuracy 1 becomes mathematically impossible.
Impossible.
Yeah. The necessary information simply cannot be encoded reliably enough into that single output stream to fully resolve the uncertainty of the query. It's framed as a fundamental limit, almost like physics, for the single-pass reasoning structure.
That is profound. So if the capacity dollars is fixed, making the question more complex, increasing metadollar, is like, I don't know, trying to compress a 4K movie into the size of an old GIF file. You're guaranteed to lose critical detail.
That's a great analogy. And this certainty of failure, this mathematical impossibility of perfection beyond the threshold, leads directly to what they call the accuracy cliff.
Accuracy cliff.
And the key thing is, performance doesn't just gently degrade. When you cross that capacity threshold, performance collapses.
Yeah.
Sharply. Like water hitting its freezing point. It's a phase transition, not gradual at all.
I think anyone who pushes LLMs hard has felt that empirically. You try to get it to summarize a huge document, maybe it works, but then you add just one more constraint, and categorize everything by date and source type.
Right.
And suddenly the output is just complete nonsense.
Yeah.
That's the cliff right there in practice.
That's a perfect example. It really is. They define 2 regimes based on this. First, there's the capacity sufficient regime. That's where the demand beta is, less than or equal to $$ plus 1. In this zone, accuracy can be perfect, performance is stable, the model basically has the bandwidth it needs.
Okay, safe zone. But the moment we step over that line,
That's when you enter the capacity overflow regime, when beta is greater than $0 plus a quarter. And this is where the performance ceiling just collapses. The maximum achievable accuracy immediately starts decaying hyperbolically.
So fast.
Very fast. It's governed by the ratio $1 plus 1 beta. To make that practical, if you increase the information demand but a beta by just say 50% beyond that capacity limit, your maximum possible accuracy ceiling could easily drop by 1/3. It's a really steep, rapid decline in reliability.
Wow.
And crucially, they argue no amount of clever prompting within that single pass can fundamentally override this hyperbolic decay once you're over the cliff.
That really highlights the risk, doesn't it? Relying on these single-pass models for critical, high-complexity tasks feels inherently dangerous if this cliff exists. Was this just theory, or did they actually show this happening with real models?
Oh, they tested it rigorously. They used models like Qwen 314b and Qwen 38b, and they systematically cranked up the information demand at beta by doing things like increasing the context length or adding more reasoning hops.
Man,
And the empirical results lined up almost perfectly with the predicted theoretical capacity curves. As soon as the demand crossed that calculated threshold, boom, performance just plummeted. It completely validated the accuracy cliff idea.
that's fascinating, especially when you think about techniques we use all the time, like chain of thought prompting, TOT, or self-consistency, SC. We use them because they seem to make the model reason better.
Right, they definitely help.
Does this research say those are just, I don't know, delaying the inevitable fall off the cliff?
That's exactly the insight the analysis provides. AT and SC do improve performance, sometimes significantly. But the reason why they work, according to this theory, is that they effectively increase the model's usable single-pass capacity, CTL. By forcing the model to sort of write down its thinking steps, they make the information flow more explicit, more structured, maybe more efficient within that single pass. So they push the onset of the cliff further out. They make the model more resilient up to a higher level of complexity.
Okay.
But they don't eliminate the fundamental constraint. They just give you a slightly bigger glass, but the amount of water you're trying to pour still determines if it overflows eventually.
Okay, so this single pass problem is already bad because of this fixed capacity of dollars. But let's get to the second part of the crisis you mentioned. Why is multi-hop QA specifically almost designed to push LLMs off this cliff even faster? What makes that demand shoot up so quickly?
Right. The core problem is baked into the structure of multi-hop reasoning itself. You have this chain, right? $, right arrow, Z1, right arrow, Z2, right arrow, dots, right arrow, right. Finding one piece of information depends on the previous one.
Mm-hmm.
This necessary sequence creates what the paper calls a dual interlocking crisis. It sets the stage for both generating errors and guaranteeing they get amplified.
Okay, let's break that down. Crisis number one again was stepwise capacity overflow, focused on how the demand grows.
Exactly. The complexity just compounds with every single hop. The information demand, but it doesn't just grow linearly with the number of hops. No, the modeling suggests it grows superlinearly, potentially even exponentially with the dollars. And it also scales linearly with the context length. Dollars. Because think about it, the output of step Z1 needs to be perfectly understood and integrated into the context for step Z or 2.
Yep.
So the complexity of managing that evolving state just escalates really, really quickly. A 4-hop question isn't just 4 times as hard as a 1-hop question. It's potentially much harder because you have to track all those dependencies accurately. This rapid scaling is what drives the model straight towards that accuracy cliff.
Okay, that's the demand explosion. And crisis number 2, cross-step error accumulation. This is why even one tiny mistake early on becomes a total disaster later. The amplification problem.
Precisely. That sequential chain structure acts like a perfect error amplifier. It's like following a complex baking recipe. If you make a mistake in step 1, say you use salt instead of sugar.
Oops.
Yeah. Every step after that, no matter how perfectly you execute it, the final cake is ruined, right?
Totally.
Same idea here. Even if the model makes only a small error on a single step, let's say the per-step error rate, epsilon dollars, is tiny, maybe 3%. The overall probability of succeeding across the entire chain decays rapidly with the number of steps, k plus 1.
And there's a formula for that decay, too, isn't there?
Yep, and it's pretty brutal. The probability of success is bounded by $1 epsilon, k plus $1.
So $1 epsilon to the power of the number of steps.
Right. Think about it. If you have, say, 5 steps, k plus 1 equals 5, and a model that's actually quite good, 97% accurate on each step, epsilon equals 0.033, your chance of getting the whole chain right is already down to about $10.97, which is only around 85%.
Wow, just from 3% error per step.
Exactly. And for tasks needing 10 or 15 hops, that error accumulation drives the overall success probability towards 0 incredibly fast.
So the dilemma is crystal clear then. The single-pass approach is just fundamentally broken for complex tasks.
Yeah.
Because it's vulnerable to the overflow, which creates the errors, and then the accumulation ensures those errors are amplified catastrophically. You have to break that single-pass structure.
You absolutely have to, and that's the perfect setup for InfoQA, this capacity-aware, multi-call framework the researchers developed. The goal is pretty straightforward. Break the problem down, distribute the complexity over multiple controlled passes, and crucially, make sure the information demand, the bad dollar for any single step, stays well within that fixed capacity C or dollars.
Okay, so how does InfoQA actually do this structurally? It can't just be a standard prompt anymore, right?
No, it's quite different. It relies on 3 core components working together. They're designed to tackle both the capacity crisis and that error accumulation crisis. The first piece is capacity-aware task decomposition.
Decomposition, okay.
Instead of just throwing the whole complex multi-hop query at the LLM all at once, the system actually breaks it down into a sequence of much simpler, ideally single-hop sub-questions.
Okay, let's use our Dune example again. How would that break down?
Right, the original complex query. What is the birth date of the lead actor in the movie directed by the person who wrote Dune? InfoQA would first decompose this into maybe just, based on the context provided, who wrote Dune?
Ah, much simpler.
Much simpler. This decomposition makes sure that the information demand for just that one isolated step is low. It stays within capacity dollars. So you avoid the capacity overflow problem at that micro level.
Okay, that handles keeping individual steps manageable capacity-wise. But how do they stop the errors from compounding? How do they make sure step 2 reliably uses the answer from step 1?
That's where component 2 comes in, the dependency explicit workflow. This is all about making the link between steps robust and explicit to fight that compounding crisis. Instead of just hoping the LLM remembers the previous answer in its internal, potentially noisy state, the process is externalized. The current state of the reasoning, the findings so far, are explicitly passed forward by literally rewriting the query itself.
I see. So when the LLM answers the first sub-question with, say, Frank Herbert, the system doesn't just note that down somewhere. It actually uses Frank Herbert to rewrite the rest of the problem for the next LLM call.
Exactly that. The initial complex query fragment, directed by the person who wrote Dune, gets contracted and updated. The new query for step 2 becomes PopDill directed by Frank Herbert. This hard codes the dependency. It makes the chain much more robust against the LLM just forgetting or hallucinating midway.
That's clever. Okay, and the third component, iterative query contraction.
Yeah.
That sounds like the cleanup crew, making sure the prompt doesn't get incredibly long and messy after a few steps of rewriting.
That's its main job, yeah. It's the engine that keeps the information load low throughout the entire chain, even if it's long. Contraction does 2 key things, pruning and rewriting.
Pruning and rewriting.
Pruning means it throws away all the unnecessary stuff from the previous LLM call, like the detailed chain of thought reasoning, maybe redundant context snippets, basically.
Yeah.
Anything that isn't the core finding. This stops noise from accumulating. Then, contraction rewrites the remaining query into the most concise form possible using that new finding, like we just discussed with Frank Herbert. This whole process stops the prompt length from ballooning as you go deeper, which is critical for managing capacity $7 over many hops.
So it basically transforms this one big, complex, high-risk memory test into a series of short, manageable, high-confidence steps. The results must have been way better than single pass.
Oh, significantly better. MBZUAI consistently got the best F1 scores across different tests. It showed a really substantial jump compared to the single-pass methods. For instance, on those 2 to 4 hop questions using Qwen 314b, MBZUAI averaged an F1 score of 0.86.
And how did the others compare? Like self-consistency?
Self-consistency was next best, but quite a bit lower at 0.75. And standard chain of thought was around 0.73. That gap, 11 F1 points between InfoQA and SC, that's actually huge when you're aiming for reliable knowledge extraction in complex scenarios.
Yeah, that's a big difference. The overall score is impressive, definitely. But I'm really interested in the robustness part. Did it actually fix that dual crisis? How did InfoQA handle, say, more hops or really noisy context?
That's where it really shone, confirming the design principles worked. First, depth robustness, where the single-pass methods showed that classic accuracy cliff-sharp drops in performance after just 2 hops. InfoQA kept its accuracy high even as the hop count went up to 3 or 4.
Okay, so it resists the error accumulation better. What about noise?
Even more compelling, perhaps, was the length robustness. They tested it with extremely long contexts, like 8,000 to 10,000 tokens filled with potentially irrelevant information mimicking, real-world research papers or dense legal texts.
Right, the messy stuff.
Exactly. And InfoQA's performance remained stable, quite reliable, even under that heavy noise load.
And the single-pass methods. What happened to them in that noisy, long context?
They basically collapsed. Accuracy dropped to near 0 levels. That catastrophic collapse under high noise and high hop count. That is the accuracy cliff manifesting empirically. They just couldn't handle the information demand beto in that single pass.
Wow. Okay, the ablation study then must be the final piece, right? Taking InfoQA apart to prove each component was needed.
It was. It really cemented the case. They tried running the whole multi-hop reasoning chain, but forced it into a single pass, so without the decomposition step.
What happened?
Performance tanked. Average F1 dropped way down to 0.65. That directly confirmed the capacity bottleneck is real and decomposition is crucial.
Makes sense.
Then they tried another variation. Use the decomposition into steps, but don't do the pruning. Let all the past reasoning traces and thoughts accumulate in the prompt.
So let the context inflate.
Right. And that hurt performance, too. The F1 dropped to 0.78. Still better than single pass, but clearly worse than full InfoQA. This showed that pruning is vital to prevent that context inflation and noise accumulation from overwhelming the later steps.
So you need it all.
You need both the capacity management from decomposition and the careful chain maintenance from pruning and contraction to get that robust high performance on complex multi-step tasks.
This whole deep dive, it really gives us a fundamental, I think, powerful takeaway. When LLMs try to do complex multi-hop reasoning, they hit this hard theoretical limit, the Fano-style bound, and it shows up as this accuracy cliff. And the solution isn't just fiddling with prompts. It seems to require a fundamental shift in how we interact with the model, a move to capacity-aware, multi-call strategies like InfoQA.
That sums it up perfectly. We've now got a formal understanding of why single pass fails due to this capacity bottleneck, and we have a proof of concept for how to work around it. But, this work really just shifts the ground.
How so?
Well, the exciting question kind of evolves, doesn't it? It goes from why does the single pass model fail to maybe, okay, what new limits, perhaps more subtle ones, emerge when we break the task down into lots of these smaller steps?
Ah, right. Solving one bottleneck might reveal the next one. That definitely opens up new research paths. Does the source material give any hints about what we should be looking out for next in this sort of capacity-aware paradigm?
Yeah, a couple of interesting directions emerge. One big area is developing smarter, more adaptive decomposition strategies. Right now, systems like InfoQA often use a fairly structured, maybe predefined way to break down the query.
Okay.
The future might lie in making the system more dynamic. Imagine systems that can look at the query and the context, predict the complexity of the next potential step, and then adjust the size of that hop dynamically to make sure it always stays well within the model's capacity ages.
That sounds very sophisticated.
It is. And the other major frontier is applying this whole capacity-bound perspective rigorously to those really messy, high-noise, real-world domains we talked about, analyzing scientific literature where findings are buried, or sifting through complex legal cases, places where the noise isn't synthetic, it's just reality. Testing these multi-call approaches there, that will be the true test of their robustness and reveal where the next set of challenges lie.